Okay, good morning. So we continue the topic of limits and continuity. So yesterday I realized I started the theorem, I was proving the theorem, but the camera was recording the slide. So I want to start with that for warm-up. But of course, this is the theorem. Do you remember? Open set characterization of continuity. So in the lecture notes, I have written it for you as the topological definition of continuity or equivalence theorem for that. So this was a theorem that I was able to prove from 2 to 1. We want to prove that these two statements are equivalent. But for warm-up, let me just do from 1 to 2 as well together, and then we continue the lesson. So what we want to do, theorem 9.1. So do you remember when we say we have two metric spaces, x and dx, y and dy, and then I have a function from x to y, and then we want to prove that these two statements are equivalent, the statements that you see. Number one is that f is continuous. If I just say f is continuous, what do I mean? Because if you remember, I told you continuity is a local behavior. So I should talk about continuity at a given point. But when I don't write that, it means that it is continuous at every point in its domain. Yes? Okay. Sometimes we say f is continuous on x, or we just simply write f is continuous. It means it is continuous at every point. Now there is a second statement that tells you that for every v, a subset of y, but what type of subset? Open. Then the inverse image, what we learned in the first lesson of analysis, yes, the inverse image of a set is open in X. Okay, so we want to prove that these two are equivalent. Yesterday I started the hard part. The hard part is going from 2 to 1. But as I told you, I was talking, but you couldn't see the board. So let us just for warm up go from 1 to 2 today. Okay, so the proof from 1 to 2. We want to show that if f is continuous, meaning it is continuous at every point in its domain, then if I choose, so for example, if I want to give you a picture, so this is x, this is y, and f is a function from x to y, what does this tell me? It means that if I choose an open subset here, which I will call it v, and then if I pull back this v under this function, continuous function, it means that I am looking for all the points in the domain that are mapped within v under the influence of the function. So that is called the inverse image. So we want to show that if this is the so we want to show that if I choose an open set here, its inverse image is also open here. So in principle, we want to show that this set, which is the inverse image of it. How should I know this is inverse image? Inverse image means that it will be mapped here. Okay? But if I pull the open sets back, they will remain open. Something like that. Okay? So tell me, is that understandable what I'm going to say? Okay. So now I'm assuming that f is continuous, and then I want to prove this. Okay, tell me, just for refreshing your memory, where should I start from? My goal is to show number 2. What do I have in my hand? I have number 1. So this is something I hope that I could teach you. Don't get confused with what you have. You might have a lot of tools in your hand. So there is no way to understand what to do with the tools that you have. You have to start from usually what you want to prove. So my goal is to prove that a set is open. So then it means that I have to ask myself, how should I prove that a set is open? Then you know what to write. Can you tell me what to write now? I want to show that this set is open. So in principle, I should have drawn this with border lines in anticipation that this is true. Okay, so how should I start the proof? I want to show that a set, forget about its name. It's a set. You see, it's a set. I want to show that this set is open. So there is only one way to ask yourself, what was the definition of being open? So try to show that. So what was the definition of being open? It means that every point in it is interior point. So this means that if you choose any point here, you can find a neighborhood around that point which is completely inside your set. Okay, so if you think in that way, I am not saying that mathematics, of course, is hard, but if you think, if you can organize your brain to think in that way, many things becomes very simple. Okay, so we have to start. So what's the first part of the proof? I would say let P belongs to F inverse of V. We want to show that this is the interior point. So it's good to write it down for yourself, because in the beginning you don't need to write very short sentences. So let P belongs to, we prove that P is an interior point. We prove that, do you remember the symbol for interior? Okay, we prove that. This means that if I have a point here, P, it means that I should convince you that I can go around it so that this neighborhood is completely within my set. And so it means that I am looking for a number with so that the neighborhood with that radius centered P is completely here. Okay, so do you have any idea? So this is there. What is your assumption? Your assumption is that F is continuous. Okay, so F is continuous. Let me see. F is continuous. This means that F is continuous at P. Because even though P is in F inverse is a subset of X, so P is a point in X, and because F is continuous on X, it is continuous at every point. So how should we continue forward? What we have? Okay, so if I have continuity, think in this way. Continuity is a kind of operator or a machine that when you feed it with epsilon, do you remember yesterday's definition? It will give you some kind of delta. Do you remember? And that delta is what I need here, because I want to convince myself that there is some number, a small number probably, around P, so that that neighborhood is there. Okay, so it means that somehow I have to find an epsilon so that I can feed it to my continuous machine, then it will give me a delta. So is the logic clear? So now can you tell me how can I find that epsilon? So you see, I want to convince you that there is, I just want you to learn these things because these are not hard. I want to convince you that there is a delta so that if I have that neighborhood around delta, it is completely inside my set. Okay? But I intentionally called it delta. And if you know that F is continuous at P, according to what you learned, this is a good mindset. It means that you have a machine that when you feed it with any epsilon, it provides you a delta. Okay? And hopefully, if you have a little bit of experience, you know that that delta produced by this machine is the delta I am going to use there. But this machine needs an input, so it needs an epsilon, so that it produces for me a delta. What that epsilon should be? Okay, let me start. This is my assumption. So P belongs to S. So you see, is in this way, if you think in that way, analysis is a very nice subject actually. So what can I conclude from here? Yes?
That there is a neighborhood around. No, sorry.
No.
F inverse.
What the lesson one in analysis? P belongs to F inverse. It means F of P is where?
In V.
In V. Yes, that's the meaning. Okay, but do I have my epsilon now? Because what was V? V was open. And I know something is in V. So this gives me, there exists an epsilon, okay, such that the neighborhood of that centered at that point with radius epsilon is less than or equal to, is a subset of V. Do you agree? So this means that because P was here, I know that F of P is there. Sorry for the mess. F of P is there. And because V is open, I know that there is a neighborhood around it, which is there. Okay? Okay, so now, if you don't mind, let me clean this because I was confused myself. So let me clean this. I need to write it below this one. So F is continuous. This means that F is continuous at P. So you see the order matters now. I was careless. Okay, so now I have one epsilon in my hand. I have this machine that produces delta for me if I give epsilon to it. So I give that epsilon to this machine. So what can you write here? There exists a delta such that what happens for all x in x, if the distance between x and P on the x side is less than delta, then it guarantees that the distance between f of x and f of P on the y side is less than epsilon. Do you agree with what I have written? Yes? So I assume this one because my goal is to show that every point is an interior point. So from this one, I concluded that one. And I know that V is open. When V is open and this is belonging to V, it means this is an interior point. What is the meaning of being an interior point? It means that you can find a neighborhood with center that point, which is completely in my set. So it means there exists a positive epsilon. And then I have my epsilon in my hand. I have an assumption that F is continuous at P, so I can give this epsilon to this. It gives me a delta. Yes? Now I have a delta in my hand. So it's just imagination. There is nothing very concrete in your hand, okay? So this delta, I am using it. So now what do you think I will claim according to the picture I just described for you, the claim. So because it is good to write the claim and then prove it and we are done. So what do you think my claim will be? Yes?
That the epsilon is the same?
No, epsilon was here.
Yeah.
I took that epsilon, I feed it into this machine, it gives me a delta. Now I want to finish the proof. What do I need to finish the proof? I want to show that this delta is the appropriate radius around this point that I was looking for. So the claim is N P, complete it for me. Delta is a subset of F inverse V. Yes? Because if I can prove this, I am done. That's the meaning of being an interior. So I want to prove this. Okay, then again, let us review. How should I prove this? Don't think. 1 second. How should I prove this?
Take an element.
Yes.
In the neighborhood
So
and
don't
show
think. That's what I'm saying. This is a subset proof. There is no thinking about it in the beginning. So I would say let x belongs to what? The thinking will come after this. Okay? Let x belongs to this. We show that x belongs to F inverse V. Do you agree? Okay, now help me. I have this assumption in my head. So you are telling that x belongs to n p sub delta. What do I conclude from here? It means the distance from this point to the center is less than delta by the definition of neighborhood. Do you agree? But what can I conclude here? Yes, let me put a star here. Is total phrase. Yes, so from phrase, what can I conclude? I don't know about x. I know that the distance from x to p is less than delta. If I know the distance from any point to p is less than delta, according to this statement, I can immediately conclude this one. Yes? So this means that based on that statement, the y distance is less than epsilon. Yes? And then what can I conclude from here? Write it in the language of neighborhoods. What should I write? F of x. The distance between f of x to f of p is less than epsilon. So f of x belongs to a neighborhood. Which neighborhood is that? Yes?
Neighborhood of radius f of p.
Radius,
Epsilon.
epsilon,
Yes.
center, f of p. Do you agree? Okay. We are done. Do you agree? Because there is another one here. N of f of p with epsilon is itself a subset of v. Yes? If this one is in here, I can also conclude it is in v. Do you agree? So this means that I'm taking so long time a little bit because this is analysis. It's not that hard. I want you to learn these cornerstones. Okay, so what happens here? This means that f of x belongs to v. Yes? And if f of x belongs to v, what do you think I will write here? We show that what? This was the question. Are we done or not? Because if f of x is in v, where is x itself? F inverse of v. That's it. Yes? So I hope that you somehow could understand the flow. Yes? But what you need to learn in the course is to learn how to do. These are not hard theorems. The hard theorems carry some names. Those are hard theorems. It means that someone was so creative to be able to find something out of ordinary. But this is, I would say, this is an exercise. You just wrote the definitions one after the other. That is something that is expected that you learn in this course. Is there something missing? Understandable? Okay, so let us go faster a little bit now. There is another one. You might say, Babak, we learned that there is not that much difference between open sets and closed sets. Why we define continuity based on open sets, and then there is another theorem immediately there that says that the same thing happens if you work with closed sets. Okay, so in other words, if you have two metric spaces x and y, and then you have a function from x to y, again, the following two statements are equivalent. To say that f is continuous on x means the same thing as follows. For every closed set in y, the inverse image of the closed set is closed in x. Exactly this theorem, but instead of having open, we have closed. But you should be able, in principle, to tell me the proof more or less immediately. How do you think we will do that? Yes, you need to remember the definition of close, yes?
Show that the complement is open.
Yes, the complement is open. So something like that. So if, for example, let us go it in one direction. Okay, so let us go in one direction, and then you can do the other one yourself. Okay, so if you want to do this, I know that f is continuous. It means that so f is continuous. We also know that what happens, we know that f is a subset of y, but this time is closed. Okay, and then we want to prove that f inverse of f is closed. Of course, here when I say it is closed, I mean closed in the domain, codomain, and when I want to prove that this is closed in X. Okay, so that's what we want to prove. If I can guarantee this question mark, then it means that I showed that this takes me here, and then you do something similar to go backwards. That will be left as an exercise. But can you tell me what should I do? Again, don't look at what you have in hand usually. Okay? What you want to prove is this one. Okay, so you want to prove that a set is closed. The original definition of closeness, as you said, is that its complement is open. Okay, so we show that what? The complement of this one is open. But complement means what? X minus, we usually use this symbol. F minus is open. Okay? But there is one theorem that it was in the first lesson about preimages. I want to use them, might be you have forgotten, but let me write this one. So that was the theorem. F inverse of, I don't know, A minus B is equal to F inverse of A minus F inverse of B. This we had in the first lesson, so I want to use that. Okay, so I would say that X, so again, sorry, I am used to this symbol. So X minus F inverse of F. In order to use this theorem, I want to write X as an F inverse. Can you help me? So I copy and paste this one. And I ask you, what can I write X in the form that F inverse is involved? Y, yes? F inverse of Y means, tell me everything that goes to Y after F is applied on it. So if you take it back, you go back to X, yes? And now you see F inverse of a set minus F inverse of another set. This is the right-hand side of this equality. So this goes here.
Should it be F inverse X?
Pardon?
Should it be F inverse X?
No. F inverse of Y. F inverse of Y means the ones that are mapped to Y. So everything in X will be mapped to Y. So inverse image of Y will be the whole X.
The formula has A and B there, and now you have X, F, and Y.
Yes, because I am just giving names to A and B in general. So it means that if you want A is playing the role of Y, B is playing the role of F. This is a formula. I am using this formula for my sets Y and F. So I think you are confused. Can you ask me again, or I am confused? Probably I don't answer your question. No, this is a formula.
Yeah.
Okay, I am using this formula for my purpose here. I am saying that this formula is valid for any A and B. Okay, so I am writing it. So am I doing some mistakes or not?
Och det är ju X och Y och...
Det är bara att vi
Det är det som sker.
byter så att vi skriver X så att det matchar.
Jo, det förstår jag, men i formen så tar man ju inversen av A.
Is it wrong?
No.
Det är bara jag som är förvirrad.
Is it correct?
Så de är ekvivalenta.
Vi skriver X som F invers av Y.
Yes, what I'm saying is that X
För att kunna
is
använda
equal to F inverse of Y.
Yeah. Now I'm...
Yeah. So instead of X, I put f inverse of y because we have this equality. So and then we write this. Yes? And then what happens now? We want to show that f inverse of the complete is closed. Okay. Yes, everything is right. So we want to show that this one is open, and then I calculated this one, I get this one. So why this is open? This is my set. I was able to use the formula before to prove for you that this one, which we are going to prove is open, is equal to this one. But why this one is open? This is open. Why? Why this is open? Yes?
Because f is closed. And
Okay.
if we remove a closed set,
Because f is closed,
yeah.
so y minus f is open.
Yeah.
And why the whole thing is closed now? That's why the whole thing is open. Why? Because of this theorem.
Okay.
This theorem tells you that if f is continuous, the inverse image of opens is open. Do you agree? Now this is open. I agree with you because f was closed, so its complement is open. This is the inverse image of an open set. But f is continuous, this theorem, the inverse image of open sets under continuous functions is open. That's it. So there is not much to prove for that, yes? I am using the previous theorem to prove this. Are you happy or not? Is that clear? Yeah. Okay, so let us move on. Okay, this one is more interesting, and this is one of the fundamental theorems. The proof is very simple, but I want you to know that. Okay, so continuous image of a compact space is compact. Okay, so in other words, it means if I want to elaborate more, if I have two metric spaces, let's say x and y, and I have a function from x to y, which I know is continuous on x, then if you grant that x is compact, its image will remain compact. Okay? It's a very important theorem. So 9.3. So what do I have? I have a function from x to y. X and y are metric spaces. I know it is continuous. This I know. And I know that the domain is compact. I want to prove that the range is f of capital X is compact. Okay? So if you start with a compact and find the image automatically remains compact if your function is continuous. So it preserves compactness. Okay, so how can I prove a set is compact? We have two ways. Do you remember? One was the original way. I just want to remind you. And what was that? Every open cover of my set should have a finite subcover. But do you remember later in the course we learned something a little bit sometimes simpler? Yes?
Bounded and closed.
Pardon?
If it's bounded and closed.
Oh, bounded and closed. Do you remember this small mistake here? Yeah, bounded and closed was only for Euclidean spaces. If I have Euclidean space and my set is bounded and closed, it will grant me that this is compact. Okay? And there was a nice counter example for that in general this is not true. Okay, but then later we had something more. And that was sequential compactness. Do you remember? What was sequential compactness? The way that I have done it in my notes is based on the original definition. So read it yourself. Okay, but because we don't have experience on the sequential one, if you don't mind, let me just prove it using the sequential idea. So we want to prove a set is compact. So let me remind you. Okay, so if I have a set X is compact, if and only if every sequence, can you complete it for me? Every sequence in X has a sequence, a subsequence that converges to a point in X. Yes? And this is one of the theorems that I told you. I didn't prove it for you. I have the proof in the notes. It is one of the hard ones. But I just ask you to know it. It's important. There are two different ways to prove that the set is compact now. Of course, three ways if it is Euclidean. If it is not Euclidean, we have only two ways. Okay? One, the original definition, and one, the sequential definition. Okay, so if I want to, I want to use this one. In the notes, you can see the original way. Okay, so I would say, okay, if I want to do it in that way, my target is to prove that this is compact. So what should I do? I would say let Yn be a sequence in f of x. Just to remind you, we show that, can you complete the sentence for me? I want to see if you understand. We show that what? Yeah, read this again. What should I show? I want to show that this set is compact, and I want to use this idea. So this is why I picked a random, an arbitrary sequence in my set. We show that, yes, Yn has
A limit point, or a converges to a point.
no, it has a subsequence.
Oh yeah.
Subsequence that converges to a point in what? F of x. Okay? This is what I want to do. This is in principle in math literature, you don't need to write this. This is why the books are not very understandable, because they just put the sentence after the sentence. Okay? But if it's good in the beginning, you write this down. Okay, so now what do I have? So for every n, because this is a sequence in fx, can you tell me what happens? So for every n, we know that Yn belongs to f of x. What does it mean? Because Yn is in the image of f under x, f acting on x, it means there exists an element in x such that, complete it for me. What should I write? So I am saying that I would say let n belongs to f. Okay? Yn belongs to f of x because my sequence, by my assumption, is a sequence in f of x. It means all the terms are in f of x, including y sub n. Y sub n belongs to f of x. It means there exists an element in x such that f acting on x is Yn. Yes? That's the meaning. I'm just writing the definition, so I'm doing nothing. Okay. And now what happens? Therefore, so then x sub n is a sequence in what? In x. Do you agree? Because you gave me a sequence, I tried to find an element in x so that f of xn is equal to yn. So it means that I am constructing a sequence, a new sequence, but this new sequence lives in x. Okay? So now tell me, how can I prove it? Okay? So x is compact. X is compact. Yes? Xn is a sequence in x. From these two, what can I conclude? Again, using this reminder. Okay, what can I conclude? Yes?
Xn has a subsequence.
Subsequence, yes. So it means that there exists, let me be a little bit sloppy because of time. There exists a subsequence of this one in X. There exists this subsequence such that what? X n sub k converges to a point in X. Is that right? So you gave me a sequence in f of x. Using that sequence, I constructed another sequence in my domain, but my domain is compact and my sequence is in my domain, so it means the existence of such a subsequence is granted, so that this converges to a point there. Okay, but finish the proof now. It needs a theorem from yesterday. I have a sequence that converges to x. The function f is continuous. Okay? X sub nk converges to x in x, converges to x, and this is in x. F is continuous. Can you finish it? You remember, if I have a sequence that converges to a point, the sequence of f's will also converge to f of the point because of continuity yesterday. So this means that f of xn sub k converges to f of x. Yes, I don't remember which theorem yesterday. Yes.
9.5.
9.5. 9.5 yesterday. Yes, thank you. No, this is not 9. Oh, that was a little bit.
No,
mistake.
9.6.
No, but you are right, because this I have forgotten to, I have to change this to 10. This is 10th lesson.
Okay, 9.16.
9.16. So, yeah, but don't get confused. Unfortunately, I forgot to change the numbering. Every number 9 should be 10 in this lecture. This is the 10th lecture. Okay? Anyway, we are done. Because I was looking for a sequence, we show that. Why is that? Because what is this one, by the way? This is yn sub k. Yes? And it converges to f of x, which belongs to y. Now I forgot, unfortunately, to change the number. So is that understandable? And you see that if you go to my proof in the notes, the open cover definition is a little bit harder. So this is a good exercise that we didn't do some exercise on this definition of compactness, but this is one of the exercises that you can see it is easier to do it. Any questions? Understandable? Okay, hopefully yes. Okay. So this is also a definition. We already had that, bounded mapping. So what do you think a mapping is bounded? So for example, when we say f of x equals to sine x, it is a bounded function. Why it is a bounded function? Because its range, sine x, will not go above 1, will not go below minus 1. So when I say that a function is bounded, what I care is about the range of the function. The range of the function is a bounded set. Okay? But do you remember the notion of boundedness in just generic metric space is a little bit subtle because we don't have the notion of order there. So we have to come up with the same idea. So do you remember what I told you about a bounded subset of a metric space? How should I know that a set is bounded in a metric space?
You take an M and then circle around it.
Exactly. So it means that I can have a neighborhood around the set. Yes? So that's the meaning of being bounded. And I have written here for you the exact definition of boundedness. But that is the exact idea. But now there are two very important but very simple theorems that I want you to know. If I have a continuous function on a compact set, it is bounded. It's a very, very simple theorem, but very important one. So let me correct the numbering from now. So this will be 10, 5. Okay, I will fix it later for you. So what does it mean? It means that if I have a function from x to y, and I know that it is continuous, and I know that x is compact, I want to prove that f of x is bounded. Okay, can you tell me why? So proof is very simple.
Because we know that if f is continuous, then y is compact as well.
So let me write it. F is continuous, x is compact. From these two, what I can conclude, this is this theorem. What was that theorem? 10.3. So what's the conclusion?
That y is compact as
The
well.
f of x
That's right, yeah.
is compact. Okay? And then?
All compact sets are bounded.
Yes, that's bounded. Yes, let me repeat for you here. So if k is compact, so this is one of the important themes actually for this course. If it is compact, then k is bounded and closed. Okay? So go and study that one. So I'm giving you exam questions, okay? So this one, k is closed and bounded. But do you remember the reverse in general is not true, but the reverse is true if I have Euclidean spaces. Okay? So remember, this is a very important fact. So in general, if my k is bounded and closed, I cannot guarantee, and I have given you a counter example in the notes, which is very simple. Okay, so you can go and study that. In general, this is not reversible, but in Euclidean space, it is also reversible, so they are equivalent. Okay, so now that I know f of x is compact, I can conclude that it is closed and bounded. Closeness is not wanted in this theorem, but boundedness is what I so that's the proof. Is that right? Okay, so now the next one, if I go to the next one, this is what you learned in calculus as max-min theorem. Okay, in this case, again, because if I want to use inequalities in the values, I have to make sure that the right-hand side is ordered. So this is why it does not work in a generic metric space. I am using R here. So what does this tell me? This tells me that if x and dx be a compact metric space, if f is a function from x to r continuous, then my function attains its maximum and its minimum. In other words, there will be points p and q in x such that f of x is always greater than or equal to f of p and less than or equal to f of q for every x in x. In other words, f attains both its minimum and maximum. So this is what you learned in calculus, even though it was very trivial, but this is one of the theorems that you couldn't prove it when you were studying calculus. So this is why, because it was intuitively correct, you accepted that, but this is the proof, and the proof is just one line now, because we have developed a lot of tools in our hand. Can you do it for me? Can you finish it? Let us try to understand that. So this is 10.6. So what we have, this time, f is from x, not to any generic this one is metric space, but this one is R with Euclidean metric. And I know this is continuous. So my goal is to show that f of f attains its max and mean. Something like that. Okay, so how should we do that? Sorry. One important part is that X is compact. So if I have a real valued function on a compact set, then F attains its maximum and minimum. Why is that? Because, so let us do that. F is continuous, X is compact. What I can conclude is that F of X is bounded. Yes, which theorem? 10.5. Yes. But now this set is where, because the output of my function is a real number, this is bounded in R, because the outputs are in R. So this means that F of X is a subset of R, and it is not empty. The reason it is not empty, because I'm assuming that X is not empty. Why? Because a metric space cannot be empty. Okay, so metric space is not empty, so this means this is not empty. Okay, so F of X is bounded. F of X is a non-empty subset of R. What I can conclude from here, the completeness axiom, what does it mean? Do you remember? So today you don't have your memory with you, yes? Why is that? Yes. Okay, so if I have a subset, if a non-empty subset of the set of real numbers and bounded, it has a supremum and it has an infimum. Yes, that was the axiom, the completeness axiom. So it means that F of X has sup and inf. Okay, so let little m be infimum and capital M be the supremum. Yes? But what I want to show that my function attains its maximum minimum. Supremum and infimum are good, but not good enough, because there is no guarantee they are attained. I want to show that they are attained. But can you tell me why this little m is a limit point for F of X? So let me talk about supremum. So if this is R, F of X is a bounded subset of R, somewhere here. This is your F of X. And this is your supremum. Okay? My question is that, do you agree that this supremum is a limit point for F of X? Why? Because any neighborhood around that will contain as an element from my set. Yes, do you agree? So this means that M and M, both of them belong to Fx prime. Yes, because any neighborhood around this M will contain some point from my set, and this one is the infimum. Any neighborhood around that will contain some point from my set as well. Okay, so I hope that I could convince you that it is true. Yes, but now I want to say something more, and I want to wait for you. Okay, so hopefully your memory starts working by the last minute of today. Yes. So why I can conclude that? Because it's closed. Very good. Yes. Why it's closed? Because it is closed. Your memory is coming back now. So f of X is compact. When it is compact, it is closed and bounded. In the previous theorems, I didn't use the closeness, but now I want to use. So why, if this is closed? Because f of X is closed. Because if it is closed, it contains every limit point of itself. That was a second characterization of it. So that's it. So it means that they are supremum and infimum, but they belong to my set. So this means that they are maximum and minimum. Is that right? Yes. Yes or no? Yes. Okay. So okay. So let me stop here and start preaching you. Okay.